tissue from cancer patients. And using this tissue, we are in the process of establishing India's specific cancer genome database. This cancer database will help you to understand or identify the biomarkers specific to Indian population for a better management of cancer situation in India.
A final year BTech student at IIT Madras. I am also the CEO and co-founder of the E-Plane company.
I've chosen this institute because it is one of the top leading institutions in India.
Academics is something which is the most important thing at IIT Madras.
One of the most prominent sections of my institute life is doing courses. I have done courses right from sociology to history to politics and as well as in finance.
Whatever you study here, you feel it's, there is a lot to learn in that field and there is a lot which can come out of that field.
As a student in IIT Madras, I was given the opportunity to consult with industries as well as do research work.
We also want to then start working on electric air taxis in about 1 or 2 years' time.
Here in IIT, the best thing is you can actually know whether you are passionate about this or not, because you'll have the time and also opportunity to explore each and everything.
Despite being a business student over here in IIT Madras, the uniqueness over other B schools in India is that I get to network over with the people with other departments as well.
It is no wonder that in the last 5 years, the major technology startups that have made headlines in India are from IIT Madras.
It's a great place for students to enhance their learning.
Chennai transports almost 800 million liters of water every day, out of which only 400 liters is being charged. Other 400 million liters per day is lost.
Headlines in India are from IIT Madras.
It's a great place for students to enhance their
From our survey, we found that most of it goes into leakage, and since the pipelines are underground, there is no way of telling the leakage is out of which only 400 liters is being charged. Other 400 million liters per day is lost.
Sorry, some technical issues. Sorry, Rudra, take over.
Yeah, thank you, Shivram. So, sir, we'll wait for 2 more minutes. We can just start the event exactly at 5:45.
Okay.
Shivram, you can just share the poster if you can.
Yeah, sure. One second.
Hello, MSR. How are you? MSR has joined.
Satyam, good evening. Muru here.
Murugan, you managed to join as well. Great.
Yes, I just finished the class. Yeah.
Yeah, Satyan, I'm fine.
Cool.
I just sent the link to Gandhiram also.
Yeah, I had also. He said he'll try and join as well. Yeah.
I think he has joined there.
Okay.
Yeah, I have joined. Thanks.
Hi, Ram. Oh, yeah, there
Hi.
you are. Yeah, okay. Sorry, I didn't recognize you. With your mask on.
Yeah.
Yeah, thanks for joining in early. You are there in the West Coast.
No problem. I'm usually early here to the lab. So.
Okay, cool.
About 5:30 a.m. there.
Yeah, my schedule is 4 to 7, and then school kids pick up, drop off, and then come back in the afternoon. So.
It's good.
Professor Satyam will start.
Okay.
Yeah, go ahead. Yeah.
So, hello and good day to everyone. Thank you for joining us today. This is Rudra from the Office of Global Engagement, and it's my pleasure to welcome you all to the 63rd webinar from the CIRIS webinar series. So, the Institute of Eminence scheme was launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutes. IIT Madras is proud to have been selected as one such Institute of Eminence. So a total of 68 research initiatives belonging to 21 identified technology cluster are presently underway at IIT Madras. As a part of these initiatives, the IRIS webinar series aims to showcase the innovative research that is being generated to various stakeholders like students, researchers, industrialists, and policymakers. So from the advanced manufacturing cluster, this research initiative is being presenting today is titled Extraterrestrial Manufacturing, which is called as XTEM, led by Professor Satyan Subbaiah. So to introduce Professor Satyan, the speaker of today's program, Dr. Satyan Subbaiah is presently serving as the Associate Professor in the Department of Mechanical Engineering at IIT Madras. He obtained his MS degree in the University of Illinois, Urbana-Champaign, USA. He completed his PhD at Georgia Tech Institute of Technology, USA. Later, he worked with Singapore Institute of Manufacturing Technology, which is called SIMTech, an A-star research institute for about 6 months before moving to NTU in 2007. He was with NTU until May 2014, after he joined IIT Madras as Associate Professor. He published 70 plus papers and filed patents, and his research interests including machining, grinding, polishing, tribo emissions, manufacturing in space, and graphene exfoliation. He is presently an investigator of the projects Unmanned Robotic Drilling, Hybrid 3D Printing, and machining of metals. HPMF CVD coatings in microgravity environment, recycling chips and foils into feedstock, and diamond crystal in extent. Also, we have Dr. Malshe, who has joined as the moderator of today's program. Well, Dr. Ajay Malshe is R. Eugene and Susie E. Goodson Distinguished Professor at the School of Mechanical Engineering, Purdue University. He has 25 years of academic scholarship and 15 years of partly overlapping nano manufacturing business into entrepreneurship, experiencing taking breakthrough ideas from the tabletop to factory floor as a founder, CTO, and board member of Nanomech Corp. He is member of professional organization including ASEE, ASME, CARP, NAE, SME, and several various roles. Subject of his competences are smart, human-centric, convergent manufacturing, bio-inspired designs, multifunctional materials, and system integration. Application areas of experience are heavy-duty machines, microelectronics, smart food manufacturing for equity, and space manufacturing. He has 27 allowed and pending patents. More than 60% are licensed, resulting in commercialized product for leading aerospace, automotive, energy, heavy-duty trucking, racing, and other smart and precision manufacturing industries. Dr. Malshe received more than 40 international recognition, including the member of National Academy of Engineering, and also like SMU Research Implementation Award, and the 20 most influential professor in smart manufacturing recognition, and fellowships of the American Society of Materials, the American Society of Mechanical Engineering, the International Academy of Production Engineering, and the UK's Institute of Physics. He has trained and mentored more than 1,200 scientists, engineers, and entrepreneurs. Also, it's a great pleasure in welcoming the other PIs, co-PIs, collaborators, students, and researchers. So before we start, a note to the participants, please use the Q&A box to enter your questions, and please like or upvote the question that may interest you so that the moderator can prioritize them. Over to you, Professor Satyan.
Okay, great. Thank you very much, Rudra, for the nice introduction. Greetings to all present here, all the panelists who are here, my colleagues. Greetings to Professor Ajay Malshe. Thanks to Ram for joining us from California, and all others, and also the audience. Greetings, one and all from IIT Madras, especially from XTEM. So I'm just going to share my screen. Just 1 second, please. Okay. Just 1 second. Sorry about that. Yeah. Okay. I hope you can see my screen, and my audio is also okay. Yeah. So what I will do is I'll just give you a brief idea of the extraterrestrial manufacturing group that was just formed here this year, earlier this year, and then we'll introduce you to the activities that are happening here. We think it's an exciting topic of what Ajay Malshe calls in-space manufacturing. We are calling it XTEM here. So I'll just give you an idea of what's happening over here. Yeah. Okay, before we start, Ajay Malshe has requested me to post 2 questions for the audience. These are questions that you can think through as we are going through this webinar, and you can post your sort of answers in the Q&A box as well. So he has posted 2 questions, and he will take these answers up and the questions up later when he's going to moderate the session. Question number 1 is the audience is requested to think of and share one impossible moonshot application for in-space manufacturing. So what we're calling as extraterrestrial manufacturing is the same as in-space manufacturing. So what could possibly be one almost impossible moonshot application? Moonshot is an extremely ambitious project or mission undertaken to achieve a monumental goal, is a definition of moonshot. So that's question number 1. Question number 2 is discuss at least one knowledge gap that will enable manufacturing to happen in space. Yeah. So question number 1 is describe or give a possibly impossible moonshot application. Second one is discuss at least one knowledge gap that is preventing in-space manufacturing from happening today. Yeah. So please post your answers in the Q&A section, and Professor Ajay will take this up later in the talk as well. Okay. Okay. So quickly, here's a rough plan of what we have today. So I will introduce you to XTEM, what our perspective of extraterrestrial manufacturing. And in that, we have 3 verticals. So I will introduce you to vertical A and B, which is listed there. And then I'm going to request Amit, he's our microgravity expert here. So he will talk about microgravity and the cool stuff that's happening in our campus here, the setup that we have that can actually simulate microgravity. After that, I'll hand over to Ajay, who will take up these questions, and then he will steer the discussion towards the end. Yeah, so that's roughly the plan for the webinar. Okay. Okay, so first question is, what is XTEM? What is it that we're doing here? And extraterrestrial manufacturing is also called as ISM, in-space manufacturing by Martian. Okay. Okay, so the idea of space, if you look at space-related manufacturing, we do a lot of what is shown here in the gray box here, make in Earth for space. Yeah, so we do a lot of that here. So we make whatever we want here, rockets, satellites, panels, etc. We put them together. It goes off into the space, and there's used over there. Yeah. So we are looking at the other 2 questions. How can I make in space whatever I want to use in space? That's shown here as make in space for space. And also we also have to ask the question, can I make stuff in space and bring it back to the Earth so that we can actually use it on the Earth as well? So our XTEM group is trying to take some baby steps and probably fly as well in these 2 spaces, which is make in space for space and make in space for Earth. Yeah. Okay. So so from that context, we have organized ourselves into 3 verticals. The verticals is shown here as A, B, and C as well. So the vertical A talks about manufacturing in space for space, and there again we have 2 sort of sub verticals. If you have to do a settlement in planets, you have to mine raw materials, you have to make use of the Martian lunar soils. So we have some projects that we have sort of envisioned and started working on is so-called A1. And A2, we have a lot of projects that is, how do you make stuff on board, whether it's a spacecraft, whether it's a space station that is orbiting the Earth, or you're just traveling for a long amount of time. And also related to that is recycling material on board as well. In vertical B, we have manufacturing in space for Earth. So there are certain things that can be manufactured better under microgravity. So can we take raw materials to space, make things over there and bring them back to the Earth? Examples are possibly metal foams. So Professor Shankaran is working on this. Crystals, diamond crystals, Professor M.S.R. Rao, and optical fibers possibly, and also bioprinting as well. So this is sort of some of our future projects that we want to work on. And supporting all this is an important vertical C, which is microgravity tests, and which Professor Amit will talk about later. So we have a nice 2.5 second drop test facility here on campus that we're going to use, and we're hoping to do some parabolic test flights as well if we can, muster the resources for that. And there are also some other things that we could possibly look at in terms of PS4 platform from ISRO as well. So this is sort of how our extraterrestrial manufacturing research is structured right now. So we have a nice team, a mix of engineers from various fields: aerospace, mechanical, civil, metallurgy, materials as well. And also we have some scientists on board from physics, chemistry as well. We also have some industry collaborators. Space Foundry, Ram is here, join us here. And then we are looking to work with Fabhead and E-Plane at some point of time as well. And we have hired some very talented staff. So we have some Niket, Aditya, and others are here. And also we have some PhD scholars working on it. We also have collaborating with JNCSR, and we have some international collaborators as well, including we are hoping to rope in Majay Marche very soon as well. So these are the people, the faces that you don't see. You're seeing my face, but behind the scenes, all these people are all working. This is the real team that's actually doing all the work. Yeah. So more people. And this is the staff. We're working on it. And then we have our collaborators. I've listed them as collaborators. With a lot of discussions are still ongoing in terms of how to actually engage with them. So we're hoping to rope in all of them, including Ajay as well. And then we have Divakar, who's going to give us our next space talk very soon. And then we have Ram here, and we're going to hopefully rope in Fabrics and E-Plane as well. Okay, so I'll just give you a sort of a quick overview of these projects. So for example, I said vertical A. Vertical A was manufacturing in space for space. So under that, A1 is deals with human settlements. So whether you're going to, let's say there's a lot of efforts going on by different countries to explore Moon, Mars, asteroids, and even do some settlements possibly. So for that, you have to use materials for construction. So we have our colleague Piyush. Unfortunately, Piyush is not able to join us today, but he's working on Martian Concrete. So he's got some similarities. I'll show you some pictures later. And then we have Professor Prabhu Rajagopal, my colleague, is working on unmanned robotic drilling aspects as well. So together, myself and here, we're trying to figure out how to develop robotic drilling aspects as well. And then we have the A2, which is making things on board using 3D printing, whether it's plastics or metals. And with metals, we want exploring a more of a hybrid combination of 3D printing and machining. And then we have Professor Rao's group, who's he's an expert in diamonds. So we're trying to figure out how to make use of some of the resources already available on board, such as methane and hydrogen, to see if we can actually do some coatings on board as well. And then we have Professor Arunachalam and group looking at Institute of Optics Fabrication. And then we have my colleague Ratna Kumar looking at fabricating medical diagnostics kits in situ on board. And then Sushanta and Professor Kodanaraman are working on recycling of materials on board to see if you can actually make use of materials on board. Yeah. And then we have the vertical B, which is making materials products in space. Professor Shankaran is looking at foams, metal foams like sponge. I'll show you some pictures later. And then the diamond crystals again with Professor Ramachandra Rao's group. Yeah. And then Amit will talk a little bit more about this, which is microgravity tests. So this will support these verticals as well. Yeah. Okay. So quickly making space for space. So I only have a minute or so here. I'm going to hand over to Amit soon. So we have the Piyush looking at space concrete. So the bottom three pictures that you see are made in his lab. So this Martian concrete, we actually bought Martian simulants, and then he's actually trying to make them into concrete. So these are actual samples made in his lab. I would say hot off the press in the last couple of weeks or so. So we're trying to see how what kind of strength these kind of this concretes will have. How to make this concrete without the use of water, for example. What other kind of binders can be used to put these materials together as well. So this is some cool stuff that's happening in our labs. So unmanned drilling robots. We already have a very strong student teams that have built several unmanned robots, and including in Prabhu's group as well. So we're trying to see how we can use this to do some drilling, automated drilling, something that's already happening in some of the rovers in Mars today. So we are trying to see how we can actually complement their efforts as well. The vertical B, which is making in space for Earth. So we have Professor Shankaran's lab here. We're trying to make some metal foams. So metal foams are like sponges. So if you're familiar with sponge, we're trying to see these are actually plastic or polymers that is made into this. So here we can actually make metals also in the same way. And it turns out that there are some advantages in making these metal foams without the influence of gravity, for example. So Professor Shankaran's group is working on it, and we hope to have some cool stuff going very soon as well. And then we also have Professor Ramachandra Rao's group. We have tapping into his expertise to see how we can actually make some of this stuff in space as well. How do you actually grow diamonds in space? And this may require long-term experiments in terms of parabolic flights and so forth, but we hope to do some very preliminary experiments in our 2.5-second drop test facility as well. Okay, so now I'm going to hand over to Professor Amit. So he's going to tell us some cool stuff about what's happening in terms of microgravity and what we can actually achieve in our campus as well. So over to you, Amit. I'm going to stop sharing and you can take over. Yeah.
Okay, just let me know if you can see my slides.
Yeah, we can see it. Yeah.
Okay, thank you. Thank you, Professor Satyan. I'm just going to present something about the Microgravity Doctor, which is there at IIT Madras. This was developed as a part of National Center for Combustion Research and Development, which was a Government of India initiative. And because we knew that human space program was coming, and then this area was required, and we had proposed this, and this was developed as a part of that project. So, well, why do we need something like this? Because when we have human space missions, we need to know how things behave in space environment without gravity. And, things behave very different sometimes and can be, beyond our intuition. And so for fundamental understanding of what mechanisms are there, we need to have a platform where we can do these tests. And for example, we have now a human space mission in progress in India. So we can, provide some assistance as far as safety is concerned, or, many other applications related to space mission. And where this tower again is going to be used is for space manufacturing, as Professor Satyan described. Okay, now if you go and look at, broadly research areas in microgravity, they are, traditionally classified into 4 areas: combustion physics, fluid physics, material physics, and biomechanics. I'll not go into details of that. I'll just jump right to our, how do we achieve microgravity environment? It's a difficult thing to achieve actually, because you have to be in space in an orbit where all the forces are balanced, and so net force is 0 on you. So that's the best place. So if you are in space station or in an orbit, that's where you get microgravity. But that is something very expensive, and not just expensive, and accessibility is also not so easy. If you have a program, then you have to plan for years together, get qualified for space. Your experiment has to get qualified before you can go there. So on the other hand, we have, there are other options which are available to us. The one which is most accessible and, accessible and where you can get a good quality of microgravity is a drop tower. Only problem with that is you have very short time. So in fact, these drop towers, we have several drop towers existing in the world. And for example, NASA Glenn Center, they call it window to space. Similarly, Japan calls it a gateway to space, because that's the first step where you can get a glimpse of how things behave in space environment. So that's the reason we went for drop tower. But because the time is less, so many experiments will require longer duration. So we'll have to look for options apart from that. So although it's a good stepping stone, but we need to move towards some other platforms where we can have a longer duration. So aircraft is one place where we can get a longer duration of microgravity of the order of 30 seconds, where an aircraft executes a parabolic maneuver, and there you can get something like 30 seconds or so. There are other alternatives, rockets, space shuttle, and recovery capsule. But as the problem with these is you have to have a proper recovery. So recovery is not easy. So these two are something which we can think of as something where we can use as we are stepping into microgravity research. These drop tower and aircraft would be the first 2 steps to look into. Okay, so telling something more about our drop tower. So this is the 5th tallest in the world right now, and you can get a gravity level of 10 to the power minus 4 G. So that's why it's called. So it's 100 micro G, and it has a capsule in capsule mode, which I'll explain to you. Because once you have, what we do is we drop the experiment from a height of 30 meters. This is a free fall of 30.5 meters. So as it's falling down, it's under, there's no force on it except for drag. Now that drag gives you a residual gravity. So by the time it falls, for example, here 30.5 meters, by the time it's falling down, it will have a residual gravity of around 0.160, which is close to lunar gravity. So to remove that residual gravity, we enclose the capsule in which we have the experiment inside another capsule, which serves as a drag shield. And so thus we are able to get a low level of gravity. So once this capsule is falling, we need to stop it also. So for which we have a deceleration mechanism, we have an airbag which takes the capsule and stops it. So where do we stand in terms of other towers? I told you we are 5th in the world, and there The tallest ones are in Germany, the ZAM drop tower, and which can give you somewhere around 9.3 if they have a catapult mode where you can shoot the payload from bottom. So it goes up and then comes down. So that way you can have around 9.3 seconds. But if you're just dropping the capsule, the experiment from the top, you get something like 4.74. The next one is in NASA Glenn.
Sorry, Amit, can I request you to go a little bit faster if you don't mind?
Yeah.
Thanks.
Okay, fine. Thank you. So that's where we are. And let me just tell you a little bit more. How does this work? Here. So we have an inner capsule where we have the experiments. This is enclosed inside a drag shield, as I mentioned. This is taken up. We cover it from top and bottom. We have front covering and tail covering, nose and tail fairing, and it's taken up. And then it's released from top. And then what you'll see is the capsule getting dropped. And on the side, you'll also see a picture of how the inner capsule is moving inside the outer capsule. That will be on the right side of the video. So there's airbag at the bottom. So you can see here, there's an inner capsule which is moving much slowly inside the outer capsule, and say you get a very good quality microgravity. Okay, that's the construction. What I just want to mention about the size of the air rack, which is around 4.5 meters tall. You can see a man standing next to him. Okay. This is our decelerator for the drop tower. We have valves over here to take the gas out or the air out. Otherwise, the capsule which falls down will bounce back. So we don't want that. So that's why we have valves to take out air in a controlled manner so that it just sinks in. So this is showing how the capsule is made ready. This is what you saw on the left side is the inner capsule, which is mounted inside an outer capsule, and the whole assembly is taken up and then dropped from the top. We have a capsule control system where data is recorded and stored inside the capsule itself, and everything is controlled wirelessly. The whole thing is. So I have just one video here showing the actual drop. This drop tower is equipped with cameras at different levels. So what you see on the left side is the camera which is focusing on the airbag, and then we have a camera which is right at the top. So you'll see the capsule coming from here and passing through this point, which is somewhere in between, and then hitting the bottom. So this capsule is somewhere around 400 kgs, 300 to 400 kgs. That's the range. Depending on the payload, it varies. And this is one of the first pictures. The candle is the favorite example people take. So when we did, this was our very first test we did. And what you see over here is the two cases. One is when you have capsule in capsule, where you have two capsules and you reduce the resistance. So you get, near hemispherical flame. When you don't have that, because of residual gravity, you don't actually get good microgravity. So that's what this is demonstrating. And what we have here is two flames. One is a candle flame, and another one is a cigarette lighter flame. And this is on the left side is normal gravity. When you push it down in zero gravity, this takes a hemispherical shape. The other one is becomes a much larger flame. So that's what there are things which are counterintuitive. We initially expected it to be something like that, the kind of flame, but it appears different. And this is again one of the initial experiments we did, where we dropped a bunch of balls. That's like around 2.5 seconds. And this is one more experiment where we are trying to study flammability of materials in space environment, because that is of importance. Because material flammability changes in a space environment. And so if we are selecting a material which is, qualifies in normal gravity, it may not still work for in zero gravity. So this is what we are studying in this. So what you see over here is a flame in normal gravity. The blue arrow which you see is where the drop starts, and you see a change in the flame. And then and there's a slow motion of the same flame. This was in quiescent environment. And the same thing, if you have different flow rates, you have different images here comparing normal gravity, zero gravity. What you can see is a flame which looks much small. It's at almost double in size in length as well as width in zero gravity, and the spread rates are also higher. So these are some of the experiments which we have been doing, and we are looking forward to do more experiments for our fellow colleagues and the next time. Back to you, Satyan. Thank you.
Thanks, Amit. Yeah, thank you. Okay, I'll just continue from where I left off. Yeah, so the setup that Amit just described, the microgravity setup that we have planning to do some experiments that relate to manufacturing processes. So we have a team that's looking at arc transfer and microgravity. So with the focus more on 3D deposition, 3D printing, 3D deposition of metals. So that is one setup which in the next couple of weeks we're going to do a drop. We're hoping to do a drop. So the setup is very close to completion. Professor Srinivasu Devidula and his team are looking at machine tool structures and how they will affect microgravity. And then we have Shankaran and team looking at foaming. So again, a setup design is in progress. And for the last but one HFCVD in microgravity as well, there's some sketches and planning is going on. And finally, Priya and team, along with Professor Arunachalam and Dr. Divakar, are thinking about or working on this setup for 3D printing of polymers in microgravity. So this is the ongoing efforts here. We're also exploring parabolic flight options that will give us more time, as Professor Amit explained. So we're particularly looking at commercial services to see if we can actually use planes, such companies to zero G that offer services for this. Of course, it'll be nice if somebody in India can also do this. So if any of the audience here is willing to do a startup where they can actually do a parabolic flight and offer parabolic flights as services, so they're welcome. It involves taking a plane, emptying it all out, as you saw in the picture earlier, doing some hydraulic modifications, adding accelerometers, removing the seats, getting it flight certified, and of course, sell flight time and make money. Yeah, so that's something that we are nobody's doing in India right now. So we're hoping to have somebody in there as well. Okay, so now I've come to the point where I'm going to hand over things to Ajay. So Ajay has posed 2 questions in the beginning. So, and then I'll post some questions to Ajay, and we have posed some questions to Ajay as well. So Ajay is going to steer this discussion from here onwards. So over to Ajay. Over to you, Ajay. Yeah.
Thank you. So I'm going to share my screen.
Yeah, go ahead, Ajay. Yeah.
Let me know when you can see my screen.
Yeah, we can see your screen. It's in slide sorter mode now. Yeah.
Thank you. So once again, thank you, Satyan, and your team for inviting me. I'm actually exactly sharing the part of my presentation as you suggested that I gave about a week or 2 or a couple of weeks before.
Sure.
But the focus of my talk is not going to be non-traditional machining of diamond and diamond-like. We'll keep that for some other time, but I'm really going to focus on in-space manufacturing for factories. And part of the reason is that in your current conversation, I heard quite a bit about that 3D printing, microgravity, metal foams, polymers, so on and so forth. But this presentation would actually complement in many ways that the question is not what we will do, but first question is why we will do it. And that driver is very important. I believe there are 2 drivers. One is why we will do it, and then what is the neat physics and chemistry that is unique about space. And those are the 2 areas that I would like to harbor on. So manufacturing is about applying science and engineering, what we discover and invent, to apply it for a purposeful reason for the society. And that's what the theme of my talk will be. So this was the presentation that many years before for SME we had done, but now that program since 17-18 has moved further along quite a bit with the network of many collaborators for my group. But what we are interested in this is what we do is why we do this first, because that becomes a very important driver. So you talked about entrepreneurships and so on and so forth. And I've been an entrepreneur all my life, but entrepreneurship is not about what we do, but why we do it, and that why is very important. So first is survival, second is exploration, and third is what I call democratization. In the survival, if we take a snapshot where the world is today, we have about 7.3 billion people, and they're expected to grow to the limit that is unsustainable on Earth. So with 9.7 billion in 2050, which is not much far out, 30 years down the line, many of you will be still there. You're looking at some very staggering number. And with those staggering numbers come that most of the manufacturing, all we do today, most of the manufacturing, we use raw materials, and those all raw materials come from nature, whether it's ore, whether it's paper, whether it's water, whether it's air, whatever we do, we need a raw material. And so those all the raw materials are going to be short supply, because as the prediction is, that as in about 2050, which is somewhere here, we'll reach 9.2 billion, and this is the theoretical capacity, carrying capacity of Earth. Even if you push it in 10 plus billion people, you'll be starting to consume mostly what is available on Earth. And this is something, a real analysis. And this is something is that we need to look at, that is Earth is the only microcosm, then where we could be next. The second driver, so it is a question not of a nice thing to do, but it is a question of sheer survival for the decades to come. The second is exploration. That one thing that I find in my professional life, that most of the time students have really stopped inventing the things. And I'm not saying the inventing is the next app or a next gadget or a next device or a next 3D printing technique. I'm really talking about some real breakthrough inventions. And that because curiosity is not much challenged on Facebooks and LinkedIn. We're really going in a fast track, and it takes certain quality time. So exploring something, which I call radical innovations, is on decline right now. I mean, just to take an example, everybody hears about Moore's law. And Moore's law is that every certain years, the number of devices would double. If you look in 1955, since then the biotechnology innovations per $1 billion has declined. In the same order, in the reverse only. So exploration is very important as we explore the space, and that's something that's very important as a driver. And the last is democratization, because as much you find people applaud for the success of SpaceX, Blue Origin, Virgin Galactic, we just don't want few people to control this vast majority of the area that is far bigger than Earth. We want democratization. We really want people, average person. So I call it space equity. That this needs to be equitable to all. And that's something very important. So to do that, if you really take a snapshot at what multiple things are going on, there are a lot of activities that are still driven by the curiosity, whether it is a food, biomedical application, exploration, satellites, so on and so forth. But there are some major limitations, and those limitations are, even if I call them limitations, they're the opportunities actually. So look at the size of the SpaceX rocket and think about it. This is like me saying that you have a car or you have a two-wheeler and your fuel tank is 10 times bigger than the capsule that you're sitting in that car. Imagine a car in front of you that your gas tank and the rest of the body of the car is 10 times bigger than the 4 or 5 or whatever number of seats in your car. You would find that very ridiculous. And this is what ridiculous we are working on right now. Look at the SpaceX rocket. Just if you look at the size of the rocket, which is going to launch maybe 10 satellites, those are of the order of that can put in one warehouse, you consider this very highly inefficient system. And so the opportunities for large population to democratize it, that how going to space can be free, can be practically free. And this question might be very difficult to fathom at this point in time, but it is not surprising. As today, we buy many electronic devices, and that electronic chip is practically free. And why? Because money is made by apps, money is made by softwares, money is made by how to look up the devices. But the electronic chip, which is inside, made in a $10 billion fab lab with $70 cost, is practically free. Memory is free today. So how to go into space will be free, so what we can do there is more valuable. And so with that, the cost of payloads is going down pretty significantly in the course of time. So the vision of what we do in my laboratories and network is research supported by factories in space. Because I can speak about US right now, and this applies to every part of the world, including historically in the Silk Road. So India was connected to Silk Road from east to west. But so as the people moved, the technologies moved. As the technologies moved, the spices moved, the silk moved, and so many things moved. So today, and during that time, and even today in America, as the civilization moved from the East Coast in New York to California about a few hundred years before, the manufacturing moved on the west part of the country. So Silicon Valley is a very recent make. It used to be New York, Chicago, St. Louis, some of the Pittsburgh. Pittsburgh used to be called City of Steels. So as the human moved, the manufacturing moved, and I see that the first step for survival in the space and the growth in the space is factories in space. The word factory is actually a concept and not necessarily an entity only. What are the kind of the questions that we will drive this? And that's what I was thinking, that when it is not about what you will do, it's question first why you will do and how must to do. It is not good to do, but must to do. This is something you will have to have. So what type of products and services should be manufactured? And I would say we may not need 3D printing. In fact, one thing that is important to fathom is that in space, the space is very less. In space, the space is very less. So you really, when you talk about a circular economy, space is a perfect environment to apply those fundamentals. What type of factories will be required to produce such products? What kind of energy and material extraction systems need to be developed? The really thing need to be understand is the robotic technology that we have developed on Earth, is it the most simplest and most effective thing that we have? And something there are many students on the call, and I will pose this question to all the students. And I work in the area also called frugal engineering. Extremely inexpensive frugal engineering, because that is most accessible to the average human. And the example of this, and this is somewhat unrelated to this, but the theme is very related on the frugal engineering. If you really think that in 1819, let's go back 100 years before, 1919, the Spanish flu hit America and the rest of the world, Spanish flu, and many million people died. But during that time, the best technology that came to the rescue of billions was a mask. And 100 years later, in 2020, when pandemic hit, the best technology that came to the rescue of billions is a mask. So what is about the mask? In 100 years, if the civilization has progressed so much, why mask is the best solution? Because it is frugal. Everybody can accept it, everybody can access it, and everybody can afford it. And that's what frugality of going in space is very, very important. And that is a paradigm shift. So what type of process will be required to produce those products? What fundamental advances in our understanding of manufacturing, science, and engineering are required to scale these processes economically? And there are many other questions. So where these factories could be? They could be in orbital factory called Earth orbits. So they could be lower Earth orbit, also called LEO, or they could be surface of the moon, so or the asteroids and comets, or surface of the planetary bodies, or interplanetary spaces going beyond. So to them, what kind of industries we are talking about? So this is the new economy. According to multiple economic sources predict that in the next 30 years, this economy would dwarf internet economy. And in many ways, in industry, and it may not be 30 years, it might be 40 years or 50 years, but it is destined to happen because number of humans are increasing and per capita harvestable land is going down. So industry coverage is energy, communications, mining, transport, medicine. Ms. Howard, can we manufacture new drugs for good health care for Earth in space? I haven't heard that in the presentation. So medicine is very important. Housing, infrastructure, food and air. If human has to go in space, food has to go in space, and that food is very important. So can we manufacture food which has no water in it? And that is very difficult because water movement in the food is something very important. So these are really going to ask us the questions. Those are very, very difficult, but interesting questions for a curious mind. Factory operations would involve fabrication, assembly, repairs, storage, distribution. So in fact, a simple warehouse for products in space is an important factory that how you store and develop a logistics and supply chain for space, distribution and reclamation. This is one of the areas which is very disturbing to watch if you type on Google this space junk. How much amount of junk which is left over around the Earth is unfathomable already. So we get disturbed with plastic in ocean. I mean, we already started 10 times more than that in space already. Maintenance is another one. Maintenance is probably one of the earliest factories that would come in space because everything that goes up has to be maintained right there. It is very difficult to bring it back to Earth. So a few examples of this is stellar energy extraction, which is just unlimited source of energy that what we have there. Extraterrestrial mining, this might sound somewhat exotic. So maybe we will find the new sources of diamond and precious minerals right up there. Communication is probably the first industry that is already active, where we are connecting globe with all the internet network. One of the early pioneers in this area was Motorola with the project called Iridium, where the Iridium satellites were going to create wireless network around the Earth. That project was ahead of its time, but worth looking at what they have done. Waste, I talked about the waste. So look at this is the real map of Earth with every dot showing significant amount of junk that is around it. It is metallic, polymers, semiconductor, every sorts of it. And it's just moving around the Earth right now. This is today, when we are literally at the dawn of space century. And so how we can reclaim that is today, even a rocket has to travel, the rocket has to navigate its path by avoiding this, because even a small speck of this junk hitting any space object can be extremely detrimental. Transportation, just space tourism, is very important as well, because most of the time, recreational activities get human more excited about the end goals, and that brings the manufacturing along with it. So space tourism, along with others, is equally important. But there are some, I would say, common concern or areas to think about: safety and well-being of human operators, protection from extreme environments, because space is a very challenging environment, security of physical data and earthlings, on-site, on-demand, and custom maintenance backup systems, human-machine robotic interfaces, high-density and high-speed computing, and sustainable energy. But there are two areas that I have not included that engineers don't talk much. One is policies, and space policies are very important, because whatever we do and whatever we will work on and whatever great ideas would come, policies would dictate how to apply them. So policy is a very important area for in-space manufacturing. And second is social sciences, that how human would see the space. Means we may want to be in the space, but are we really ready for this? So social sciences is extremely important to understand the space and the insertion of the technologies. There are certain operational boundaries. Some of them you heard about the talks and excellent presentations, but low gravity, limited physical space. As I said, in space, the space is very less. because the conditions around human are very difficult. There is a good reason that I would say why God has not made human in space. We are made on Earth, but we are not made in human, and there must be a good reason for that. It's really worth thinking about that. None to little Earth-like natural resources for raw materials in space, extremely low temperatures, extremely long communication distances. The best part of the space is pictures. Those pictures look adorable. But if you think for a second how long the distance is, if we are talking about distance in India, for example, going from Chennai all the way to Delhi is a far distance. You have to take a flight. Well, that distance in space is nothing. So consider the long communication distances and very unfriendly to biology. So as a human biology and an ecosystem around us, space is very unfriendly environment. So this poses some very difficult questions for us to come up with some very exciting innovation opportunities. So at this point in time, I would like to always quote something that Douglas Adams said. The fact that we live at the bottom of a deep gravity well on the surface of a gas-covered planet, which we call Earth, going around a nuclear fireball 90 million miles away, that is Sun, and think this to be a normal is obviously some indication of how skewed our perspective tend to be. So these all difficulties that I mentioned, they might look extraordinarily difficult, but they are not, because the conditions where we live in are the perfect conditions that Mother Nature has created for us to survive. So with that, I would like to come back to the two questions to the people on the call. They think about one moonshot project, realistic moonshot project. And moonshot projects are termed quite a bit used now. But this is really a project that makes much more attractive. And one of the examples of this, years before, SpaceX worked on a moonshot project. Can I make a rocket which can be reused? That was a moonshot project, but that enabled the next step. So identify the moonshot project and discuss at least one knowledge gap. What I mean by knowledge gap. So for example, how to create, there was a good talk on waterless cement and how to make waterless cement or how to make waterless food. Or there are questions that how do you recycle that space junk? But first question, knowledge gaps, how to go and trap it, how to go and capture it. And so plastic glass in the water stream can be caught relatively easily, but a space junk which is moving with such a high speed, to just capture that is a really different technology. And there are knowledge gaps, fundamental and applied knowledge gaps. And think about those knowledge gaps, because those become a good lens for the activities that can go around you. So with that, Satyan, thank you again for inviting, and happy to be on this call.
Great, thanks a lot, Ajay, for this nice thought-provoking slides that you shared. So I welcome now the audience to post some answers to the questions that was posed. I'm just looking at there's one answer. Ajay, is interspace fueling stations on planets rich with fuel raw materials. That's one moonshot sort of a dream thing that somebody's listed here. Nitin Mukunda Kumar has listed this interspace fueling stations on planets that have rich fuel sources, basically. Yeah. So I welcome audience to post more such interesting projects, so to speak, to post here. So Ajay, what do you think of that?
So this is a good question. So and a good point that was made. So interspace fueling station, but when you're talking about the fuel, what kind of fueling station you need, what kind of fuel you need. But remember, for a fueling station, somebody has to go and replenish the fuel.
Yeah.
And the fuel that will be replenished. So think about the gas station. I'm sure you have a petroleum station close by. That petroleum station can provide a petroleum because a big tanker has come and filled that. And then it is providing to two-wheelers and four-wheelers and whatnot. So if you're going to have that fueling station, a big tanker first has to go to space, fuel that up, and then come back. So can we not think about a fuel that is already available in the space, and you don't have to refuel. You can extract it from where you are and apply it where it is need to be.
I think that's what Nitin is talking about. Sorry, yeah. I think he's talking about taking raw materials that's available in interplanetary space. So if you're going on a spaceship, you just stop by another planet, pick up the fuel, and just keep going to the next one, so to speak. Something like that is what he's talking about, I think. Yeah.
What that fuel could be?
Yeah, that's a good question. Yeah, that's a good question. Yeah. Sorry, MSR, you want to make some comments? I welcome all my other colleagues as well. Arunachalam, Murugan, Sushanta, Vel Murugan, Srinivasu, please step in and make some comments. Yeah. MSR, you want to say something? Yeah. About diamonds and what do you think we can do with diamonds in space? Here's an answer, Nitin. Titan, the moon of Saturn, has a bunch of methane gas to use as fuel.
That's true. So
now the question is that once you have the gas, how to purify it, and in what form it could be applied and plugged in. Good question. Go ahead.
Yeah, good point, Nitin. Yeah. Yeah, sorry, MSR, go ahead. Yeah.
No. If you could tap that methane, and that's a source gas for making diamond crystals,
Yeah, there you go. Yeah, diamond from methane. That's right.
That's a source gas for diamond.
There you go. Yeah.
Of course, we need some hydrogen also to remove the sp2 part, but then there's plenty of hydrogen also there in outer space.
Sure. Yeah, so Sushanta, you want to make some comments?
I have a question actually for you.
Sorry, go ahead.
Question about the methane and hydrogen. So we do have plenty of methane and hydrogen, and I was thinking about this after our seminar a couple of weeks before, that the methane that is available, what is the purity of that methane? Because if I remember from my days of synthesizing diamond, you need certain purity for methane and hydrogen to create a good quality of them, especially if you need it for the device application. The purity matters phenomenally high. So we probably need a manufacturing first to purify them, first to capture them, then purify them, then to store them, and then to supply them. So before we get to synthesis, you are going to need at least 3 manufacturing types that will get you there. And I was just reflecting on that. I would be happy to discuss that later.
Sure.
There's one more comment from Nishta Tiwari. The suggestion is to have capture these stars or sun's energy at different points in the I guess in the solar system, and then you can hop around and charge your batteries, so to speak, if you have an electrically powered space vehicle. So that's a suggestion that's being given as interplanetary charging stations. You have panels somehow pre-mounted in different places, so your spaceship can hop around and charge around as well. Yeah.
So let me pose a question along this line to all the audience: that is it doable? So right now, one of the early innovations in the electric industry was Edison, and the idea was that the houses would be connected by electric wires. And if people may not be aware about the history, Edison went to the railway companies and asked that, can I run all my electric lines along the railway lines, because we already have established the railway network, and I would exploit that to build the electric network. And the railway executives said, get out of here. This is never going to work. Nobody wants electricity. Just be aware. And so they throw him out. And this is where the railway industry is and the electric industry. So the question is, can we establish the electrical network between the space and the Earth? Because that is something very required. So you can make this solar energy, but can then transport it back to the Earth. And that would be something very required, because we are running really short of energy right now. And unlimited supply from solar to Earth would be something very realistic. Moonshot, for example.
I welcome comments from Ram as well. Ram, you're doing some cool stuff. Then it's just potential applications. So you want to make any comments on what students can do in India to become another Ram? To become another. There's a question that's asking, how can a student contribute to manufacturing in space? So Ram, what would be your answer to that?
I think that definitely there are multiple things that are there. I'm more interested in looking at mining aspects, extracting metals, rare earths, all these from space. given that mining is one of the heavily politicized topic across the world, we are going to get shortage of copper or rare earth over the next decade. It's going to be metals are going to be the next oil. I wouldn't be surprised if there are going to be wars against procuring these metals and rare earths and things like that. So like material science is something that it has not been attractive for a long period of time. So I think this is time that I think we should also look into those aspects.
Well, we have a material scientist, Professor Rao can probably comment on that as well. Mining rare earths and other precious stuff from, or even Kodan Raman, I'm not sure if he's on the call here, but he's part of our team as well.
Yeah, I think that's a way to go. A lot of mining can be done. That's what we were discussing during Gandhiram's visit last time. I think one of the, if I may say, there is a lot of onus on laser-based propulsion these days. In future, they say, you need all these rocket launches to launch these satellites into outer space. But then one of the new concepts is to use a laser power for propulsion. Now imagine if you have all these lasers manufactured in the outer space, the propulsion from that point onwards becomes much easier. You don't have to lift it all this through the gravity into the outer space. And this is going to be, I think, probably a new revolution. What do you say, Dr. Ajay? Laser-based propulsion.
Yeah, I think if you remember in my presentation, I mentioned that even solar energy pump lasers is very important. And you have abundant solar energy, and if you can pump laser, with that, you have unlimited source of coherent light.
Exactly.
Once you have that light, depending on the intensity, you can use it for deposition, writing, or propulsion. And that is something very realistic. I agree with you.
And getting the propulsion done from the already outer orbit will be much easier than doing all the ground stuff that requires a lot of energy, a lot of money also.
Also, there's a comment, Mr. which you have mentioned before in our internal meetings, is there's helium, He3, or being a valuable raw material that's found only on Moon, right?
It's complete scarcity of helium, probably except the United States, everywhere else in the world. So without that, you can't do low temperature experiments. You can't produce liquid helium for producing these high field magnets. And tapping that from the outer space could be a great, resource. Gandhiram should think about it in a serious way. Tapping the helium sources from.
Definitely. Like there's plenty in the solar, in the lunar surface. Is all.
It's all there. Helium is all there in the outer space.
Right.
Well, there's one other interesting question that is, what would you say is one concept that is at the boundary of science and science fiction as far as in-space manufacturing is concerned? Is one question is being asked. Ajay, you want to comment on that?
No, I would let that to the younger mind to think about that.
Okay.
That what could be that?
Yeah, what is that? Where is the boundary, isn't it? Yeah. Okay. Okay, I welcome other comments from my colleagues as well. Arunachalam, Murugayan. Any comments? Murugayan, you want to make any comments on?
There is a couple of questions on manufacturing in space, especially on 3D printing, and the effect of gravity is still not fully understood, especially when liquid metals behavior, how they behave. And so a lot of interesting stuff can be done, especially on force balances to on-demand manufacturing. That's what we are exploring in this project. And again, so it is uncharted word, especially in our group is concerned. Yeah.
How about Arunachalam or Siva Srinivasu, Arunachalam? Siva, you want to comment about what you're working on, your machine tool structures, and how do you think space with gravity would affect that? I'm not sure if I'm reaching out to Shiva. Okay.
Hi, Satyan.
Hi,
So
Shiva.
I have two basic, I have two basic questions to Rose Rajai. So basically, why are we not, I think same question by the student, but I'm not very sure it is the same question. But are we not tapping the solar energy to fuel some of the activities in the spaceships? That is one question. And the second one, what is the effect of low gravity on the dynamics of various equipments that we are using inside the spaceship?
So, Satyan, I couldn't hear the first question. Can you repeat it for me?
The first question was the solar energy. Are we effectively tapping solar energy to fuel the spacecrafts, whatever onboard equipment we have? Are we doing that effectively? Should more needs to be done? I think is what the question was. Second question you already heard, I think. Yeah.
Yeah. So I think the first question, you cannot say that we are doing enough. It's like in manufacturing, it is a continuous improvement, right? So I think wherever we have reached today, are there opportunities to grow? I think one of the areas to grow is storage. See, most of the time we talk about energy as a solar energy, like solar panels and others. But I think the bigger opportunity is not only capturing that, but storing and transporting. Because in manufacturing, one thing happens that the human and machines move. And as they move, the energy sources need to go with them. So mobility of energy is very important, or energy sources. So storage is going to be important as well. And the second, I think this, for the machine tools, my question is that, do we need mechanical machine tools in the space? I don't know that, because there need to be a compelling reason. And the second, in the space, what is mean by, I'm just asking some very interesting question myself, that what is the vibration isolation means in microgravity? Because when you're applying a simple milling machine, you need vibration isolation, you need a spindle. So here, can we make spindles? Those are frictionless spindles. So you can go for very higher machining speeds that you even cannot go right now. So I think this opens the envelope of very unusual opportunities that are not presented on Earth. To create those on Earth is expensive, number one, but I'm going to put a hat on, and as an entrepreneur, ask this question to everybody to think what is called MVP, M, minimum, V, viable, P, product. What could be that minimum viable product? Because cement and 3D printing and all these are nice and fun, exactly. But what gets people on in space is first tourism. And enough people have enough money to pay for going in space. So space tourist, and it might sound completely non-engineering, but that's what would get people excited about space to invest in manufacturing. So I would urge everybody to think about MVP, minimum viable product. This is just like Amazon founder. First started selling books, and one would have thought, books, who cares about books? Well, that was an MVP, minimum viable product. And now here is Amazon.com, the world's largest company. Thank you.
Sure, thanks, Ajay. Just one closing remark, which is sort of similar to what MSR already mentioned, and there's one Mohan Kumar from the audience also mentioned, is escaping the Earth is the toughest part. So whatever we can do to, quickly build some platform from which we can actually do all the launches is something that's a comment that was made as well. Okay. Okay. Any other comments from my colleagues, Sushanta or?
Yeah.
Arunachalam,
yes,
yes. Sorry.
Yes.
Yeah.
So
Hi.
one of the activities about the in situ optics fabrication, and if you think about the launch of the space satellites, the major cost associated is with the optical payloads, and we are trying to make mirrors with composite mirrors, reducing the weight and fueling the economy of launch. So what we thought is that can we print optical components in space based on the demand, so that the launch cost associated with every satellites can be reduced, and you can, in the space station, you can assemble this optical component and you can continue your mission. So, and that is one of the major thought process by which we actually trying to print optical components, and how this process will be viable in microgravity environment, and that is the kind of example in this.
Okay, thank you, Anaslam. So I think we have reached sort of we were actually well past the 1 hour mark. So I'm going to, I think we should wrap up our conversation. So thank you again for the entire team. So I'm going to hand over things back to Richu. Before that, I'll just share one quick slide, and then I will we'll wrap up. Sorry, yeah. Yeah, so thank you again, all of you, all the panelists, moderator, Mr. Ajay Malshaya, all my colleagues as well. The message I have for the audience is please join us in our efforts. It should be in our efforts. So if you want to become a student or you want to learn more stuff, you can join our group as an MSPG scholar. We will have openings in the future coming up in our team as a project staff. Of course, you're willing to collaborate. You're already doing some work. You want to work with us. We're willing to collaborate as well. We also have a space talk series. Jay gave a talk recently as well. So you can visit our website and you can contact us here as well. So there's many opportunities to actually join our efforts. So I welcome all of that. So with that, I will hand over back to our IOE office team. Yeah, so Richu is here. So yeah, over to you, Richu. Thank you. Yeah.
Thank you, Professor Satyan. And thank you to everybody on the panel. Special thank you to Professor Ajay. You've spent so much of your time spending here with us, answering so many questions, and to everyone on the panel. So thanks again to all of the audience. I know I joined a bit late, but I see there are so many interesting questions, and if we had more time, I'm sure everybody would love to answer a few more. And thanks to everybody. Thanks to all of the audience. See you all. Have a good night.
Sorry, Ajay, you want to say something, or yeah?
No, I just want to say thank you for inviting. I look forward for your participation and collaboration with Purdue.
Yeah, great. Thanks, Ajay. Thanks a lot. Yeah. Thanks, Richu. Yeah, thank you.
Thank you. Thanks, everyone.
Thanks, all of you. Ram, MSR, Arunachalam, and all my colleagues, Murugai and Shashanta, Amit, Srinivas.
Yeah,
thank you.
Thank you, Satyan. Yeah.
Thank you.
Thanks, Satyan. It's a nice session it was.
Yeah, thank you. Bye-bye.
Thank you.
Happy holidays, everyone. Thank you.
Yeah,
Bye.
sure.
Yeah,
Happy
same to you.
holidays.
Bye-bye.
Yeah, thank you.
Yes.
Bye-bye.
Bye.
Yeah, thanks, Amit, as well. Yeah.
Bye.
Yeah, bye.